In this video, we'll be factoring trinomials using two special strategies called perfect square trinomials and difference of squares. So the first trick in using perfect square trinomials or difference of squares is that we actually have to know how to find them. Now, the quickest way to find them, or at least to rule out that a trinomial is not a perfect square trinomial or a difference of squares, is to look at their a and their c values. If their a and c values are perfect squares, there is a chance that one of these two scenarios is taking place. So I like to start by looking at my trinomial and seeing, could this even be a perfect square trinomial? Now remember, perfect squares are numbers that can be perfectly square rooted, or a number that is created by taking a different number times itself. So for example, 1 times 1 is 1. So the number 1 is a perfect square trinomial. 2 times 2 is 4. So the number 4 is a perfect square trinomial. And if we continue this pattern, we find that numbers like 9, 16, 25, 36, any numbers that are created by taking a smaller number times itself to create it, those numbers are called perfect squares. So when we're looking at our a and c values, what we're looking to see is, are our a and c values perfect squares? Because if they are, we have a chance that this is a perfect square trinomial. So let's take a look at a couple of examples and at least rule out if something would not even have a chance of being a perfect square trinomial or a difference of squares. So if we take a look at this first example here, remember I'm focusing on a, which is 4, and c, which is 25. And I see here that 4 and 25 are both on my list. 4 is 2 times 2, and 25 is 5 times 5, so those are both perfect squares. So this one has a chance and could be a perfect square trinomial or a difference of squares. If I look beneath that, I see that I have 9 for my a value and 1 for my c value. And if I look over here, again, I see 1 and 9 are both perfect squares. 9 is 3 times 3, and 1 is 1 times 1. So this one, again, has a chance of being a perfect square trinomial or a difference of squares. If I look down below at the next one, I see 2 and 9, and while 9 is a perfect square, 2 is not, and that automatically rules this one out. There's not a chance that it's a perfect square trinomial or a difference of squares. If we then look over here we have a 1, which is a perfect square, but 10 is not. So again, this one gets ruled out. Now down below, this might look a little weird. You might be wondering, well, what is A, what is C? Remember, when there's no single m term in the middle, like there should be here, this is really 49m squared plus 0m, which is why it's not written there, minus 64. And now if we take a look at our a and our c values, here I see an a value of 49 and a c value of, it's 64, but negative 64 as well. So if we look at 49 and 64, those are both on our list, and as a result, this one has a chance of being a perfect square trinomial or a difference of squares. And finally, if we look down here at this bottom one, 2, I already know right off the bat, is not a perfect square, so this one would not have a chance of being a perfect square trinomial or a difference of squares. So the first piece of this is being able to rule out those problems that don't have a chance of being one of these two situations. So now let's take a look at our special patterns a little more closely. So I'm going to walk through how to factor this kind of the way we know how to factor, and then I'm going to come back and talk about this perfect square trinomial. So here you can see that we have an a and a c value that are perfect squares. And then we have a middle term in the middle that is being added. So if we see a and c are perfect squares and the middle is being added, there is a chance that this is a perfect square trinomial. And we'll show you what happens with this perfect square trinomial. So here to start, we're going to take a times c, which is 100. And we need two numbers that add to whatever b is, which in this case is 20. So we're looking for two numbers that multiply to 100 and add to 20. And when I think through those, the only two numbers I can come up with are 10 and 10. So if we take this scenario here, we have 4x squared plus 10x plus 10x plus 25. And we do our grouping, so we look at each pair. 4 and 10, their greatest common factor is 2, and they both contain an x. So if we factor that out, we get 2x plus 5 left on the inside. And then here we can factor out a positive 5, and we again get 2x plus 5 on the inside here. And then we can group 2x and 5 together. And so we end up with 2x plus 5 in the first parenthesis here, because both 2x and 5 are being multiplied by our matching parenthesis here, which is also 2x plus 5. And so when we look closely here, what we see is that we have two parentheses that are identical. And so what we can do is we can actually write it this way as 2x plus 5 times 2x plus 5, or we can write it as 2x plus 5 in parentheses squared. Now, this repeated parenthesis here is really kind of the essence of a perfect square trinomial, at least the first type. So if you look very, very carefully here, what you'll notice is that you have these two identical numbers. You have 2x plus 5 here, so we have a 2x and a 2x, and we have a plus 5 and a plus 5 here. And if you go back and look closely at the equation, there's a really special relationship going on here with this equation. So first, we have 4x squared. And if you square root 4x squared, the square root of 4 is 2, and the square root of x squared is x. And if you notice, that's the first number in each of these parentheses. Then from here, if you square root 25, you're going to see that the 5 is the second number in each of these parentheses. Then the middle number here also has a really special relationship, because if you take 2x and you multiply it by 5, you get 10x. We see two 10x's here in the problem, and so if we multiply 10x by 2, that gives us 20x. So in order to determine if we have a perfect square trinomial, we're first going to look and see, can a and c be perfectly square rooted? If they can be, we're going to square root them. And then we're going to test out and see if the middle term meets the requirements for a perfect square trinomial, which in this case would mean that we would take the 2x and the 5, and we would multiply those together. And then we would double that. And if that equals our middle term, we have a perfect square trinomial. And then what we can do is we can jump right into factored form here. We have the 2x, we have the 5, and we can factor those right away. So we'll practice those as we go through a couple of examples. Now the second type of perfect square trinomial is very similar to what you saw in the first slide over there. The only difference here is that this middle term here is now a negative 20x instead of a positive 20x. You'll see that we still have a and c that are perfect squares, but that middle term is now subtracted or negative instead. So what I did here is I already wrote out the general factoring work of multiplying a times c add to b and then writing it out. And what we find here is that something very similar happens. We end up with 2x minus 5 times 2x minus 5. And notice that the only difference comparing the previous page to this page is that we have a subtraction symbol in the middle here. So our perfect square trinomials are really built around this idea of a and c are perfect squares. So you can square root each of them, which we did before. So we square root 4x squared, it's 2x. We square root 25, that's 5. And then from here, what we're looking for is we're looking at this middle term. And if that middle term is 2x times 5 times 2, if that's something similar to a 20 or a negative 20x, then we have a perfect square trinomial. The trickiest part about this is that, yes, we have a 2x in the front of each parenthesis and a 5 at the end. You then have to figure out, well, what's going to go inside of here? Is this going to be 2 plus signs? Or is this going to be 2 minus signs? So if it's meeting all the requirements of a perfect square trinomial, you have to look at this middle term. If this middle term is negative, you're going to have 2 subtraction signs in there because you need to have a negative 10x and a negative 10x to make that 20x here. However, if you had a positive middle term like we did on the previous slide, then you would have the 2 positives to make that middle term positive. So now let's take a look at two new examples. So here I'm going to tell you in advance, these are two perfect square trinomials. Now the way we can check is we can start by square rooting a and c. So here I have the square root of 1y squared. Square root of 1 is 1, square root of y squared is y. And then I can take the square root of 100, which is 10. So we see we have an a and a c value that are perfect squares. Now we have to test out this middle term to make sure that it checks out. So if we take 1y times 10, that gives us 10y. And then if I multiply that by 2, that gives me 20y. So while my middle term is negative, I can see where that 20y is connected. So this is a situation where it is a perfect square trinomial. So now what I'm going to do, because I know that I can factor this using my perfect square trinomial trick, is I'm going to take the 1y and the 10, and I'm going to put them into my two parentheses. I have 1y times 1y here, and then I'll have 10 and 10 here. And the last thing I have to do is I have to decide, am I going to have two plus signs in the middle or two negative signs in the middle? And because this negative term needs to be a negative 20, I'm going to put two subtractions in so that when I multiply out, I get a negative 10y and a negative 10y that then add together to be a negative 20y here. So I have my factored form right there. Now let's take a look at my second example over here. So again, we start off by double checking, okay, 16x squared. If I square root that, square root of 16 is 4, square root of x squared is x. If I square root 49, I get 7. So now I can take 4x times 7, which is 28x, and then I can multiply that by 2, and that gives me 56x, which matches my middle term here. So I can see that I do, in fact, have a perfect square trinomial. So now I can take my 4x and my 7 and put them into my parentheses. 4x and 4x in the front, 7 and 7 in the back, and then I have to decide, is this two plus signs or two negative signs? And when I take a look here, I see that my middle term is positive. Because that middle term is positive, it's going to be a plus and a plus. So now let's take a look at a difference of squares problem, which is similar, but the middle term here you're going to notice is yes, we have an a value that is still a perfect square, and yes, we have a c value that is still a perfect square. However, you're going to notice that there's not a middle term here. And what's really going on here is that this is really just a middle term of plus 0x. So you'll see in orange there that I wrote out our longhand factoring of how we would go about factoring this. And hopefully what you're noticing is just like the previous examples we saw on the perfect square trinomials, that this one also has a 2x and a 2x and a 5 and a 5 that match up with the 4x squared and the 25. The only difference here is that one of these parentheses has a subtraction and one of these parentheses has an addition. And the reason that that results is because of this middle term of 0. We need to have a positive and a negative version of that 10x there to cancel out and become 0 in the middle, which is why there's no middle term in the middle of a difference of squares problem. So when we're looking for difference of squares, we're looking for, do we have a perfect square for our a value and a perfect square for our c value, and then no middle term and just a subtraction in between those two numbers. So let's jump in and actually practice a couple of difference of squares problems. So here we can see that we have a and c values. We can see that there's no plus 0x in the middle, which I know for a difference of squares, I need there to be a plus 0 in the middle so that there's no middle term and just a subtraction. So from here, I can now check if difference of squares applies. So if I square root 9x squared, square root of 9 is 3, square root of x squared is x, and then the square root of 100 is 10. So here, because I have this middle term here of plus 0x, and I have my a value and my c value being subtracted, I know that I have a difference of squares scenario. So from here, I know that I'm going to have a 3x in the front of each. I'm then going to have a 10 in the back. And then because I want this middle term to be 0 here, I need to have one negative and one positive parenthesis. And there we go. Now if I take a look at this next one here, There's really a 1 here in front of this y, so if we square root 1y squared, we end up with 1y. If we square root 64, we end up with 8. Notice that our middle term here is 0, and there's a subtraction in between our a and our c values. So now from here, because we have a difference of squares scenario, we can do 1y and 1y, 8 and 8, and then in order to produce this middle term in the middle as a plus 0, it would just be a plus and a minus. And it doesn't matter which one is a plus or which one is a minus, it just matters that you have one of each. So now let's mix some of these together. So here we have a mixture of perfect square trinomials and difference of squares. So let's start off with this first one here. We need to square root our 36w squared, which gives us 6w. And then we need to square root our 49, or our c value, which gives us 7. So because we have perfect squares for a and c, we can then check our middle term, see if it's appropriate. So because this has a positive middle term, it's telling me that if it is one of our special properties, it must be a perfect square trinomial. And I want to check, okay, 6w times 7, that's 42w. And if I double that, I get 84w. So this is fitting of a perfect square trinomial. So from here, I now know, okay, the 6w and the 7 go into my parentheses. So I have 6w, 6w, 7, and 7. And then, because I have a positive middle term, I have 2 plus signs. Now let's take a look at the second problem over here. So here I notice that there's no middle term, unlike the first one that had a positive middle term. So this one really has a plus 0m in the middle. So I got to keep that in mind as I try to solve this one or try to factor this one out. So let's start off by square rooting our a value, which is 25m squared. That should be 5 and m, and then if I square root 64, I see that that's 8. So I see here that I do have a scenario where perfect square trinomials or difference of squares would apply. Now, because I have this plus 0 in the middle, I know that this is a difference of squares because it doesn't have a middle term. So now from here, because I know I have one of my special properties, I can put my 5m in the front of my parentheses, the 8 in the back, and then because I have a plus 0 here, I know that I have one subtraction and one addition. Now finally, taking a look at this bottom one, we see that we can square root our a value, so 100e squared, square root that becomes 10e. You can also square root the 25, which is 5. So we see we have a and c are perfect squares. We have a negative middle term, so we're going to check and see if this is a perfect square trinomial. So I check that by taking 10e times 5, which is 50e, and then doubling that, which is 100e. So I can see that this is in fact a perfect square trinomial. So now to write this into factored form, I take my 10 and my 5 and put 10e in the front of each parenthesis, 5 in the back, and then because I have a negative middle term here and need this to be a negative 100e, I know I'm going to have 2 subtractions. Finally, the last thing we're going to model here is just how we can now use this factoring strategy to help us solve quadratics. So just like our previous quadratics, we're going to start by subtracting 49 on each side because we ultimately want to use the zero product property when we factor, and to do that we need it to equal 0. So here we have 121x squared minus 49 is equal to 0. Now from here I can see that my a and my c value are perfect squares, so the square root of 121x squared is equal to 11. The square root of 49 is equal to 7. So I can tell that this is a difference of squares because we have a middle term of 0x and then perfect squares for a and c with a subtraction in between. So I now know that I can jump straight into my factored form, which in this case is 11, and this should have 11x on it. 11x and 11x, and then 7 and 7. Now the biggest and most important part here is I have to decide, is this 2 plus signs, 2 subtractions, or 1 of each? And in this case, because I have a plus 0x in the middle here, I have 1 of each. So now I've set this up using factoring, and the only thing I have left to do now, because I have a product of something times something equals 0, I can use a zero product property and solve. So here I would have 11x minus 7 is equal to 0, and I would add 7 on each side, divide by 11. So there's our first answer for x, and then finally we would solve here, subtract for 7, divide by 11, and our second answer is the negative version.